For as long as we have had minds to wonder, we have looked to the stars and dreamed of a journey. It is a dream written into our myths, our stories, and our very DNA as a species of explorers. We have conquered the continents and the oceans of our own world, and now we stand at the shore of the final greatest ocean of them all, the black, silent, and infinite void of space. The rockets that have carried us to our moon are the first primitive canoes in this great ocean. But to truly become a spacefaring species, to journey to other worlds and one day to other stars, we will need more than a canoe. We will need to build cathedrals that can sail. Tonight, we journey into the workshops of the future. We will explore the technologies, from the plausible to the seemingly impossible, that will carry humanity to the stars. Prepare for a voyage into the engineering of tomorrow. This is the future of travel. Every great journey humanity has ever taken into space has begun in the same way, with fire, with fury, and with a ground-shaking roar that seems to tear the sky apart. The chemical rocket is our modern-day titan, a triumph of engineering that has allowed us to break the chains of Earth's gravity and set foot on another world. It is the machine that has opened the door to the cosmos. But the very tool that lifts us from the Earth is also our cage. It is a brilliant, powerful, and profoundly inefficient machine, held captive by a single beautiful and unforgiving law of physics, the Tsiolkovsky rocket equation. First derived by the Russian visionary and rocket pioneer Konstantin Tsiolkovsky in 1903, this equation is the fundamental law that governs all rocket travel, and its message is a brutal one. In its simplest form, the equation tells us that to achieve a certain change in velocity, a rocket's mass must be dominated by its fuel. The faster you want to go, or the more you want to carry, the more fuel you need. But that fuel itself has mass, and to accelerate that extra fuel mass, you need even more fuel. Let's use an analogy. Imagine you are trying to climb a colossal, infinitely tall ladder, but the ladder is made of melting ice. To climb, you must generate heat to keep your hands and feet from freezing. But the heat you generate also melts the rungs beneath you. So to climb faster, you must generate more heat, which in turn melts the ladder even faster, forcing you to climb faster still. This is the vicious, self-defeating cycle of the rocket equation. The practical result of this is that a typical rocket, like the mighty Saturn V that took us to the moon, is almost entirely fuel. The Saturn V stood 363 feet tall, a true skyscraper, but of its colossal 3,000-ton mass, an astonishing 90% of it was just fuel and oxidizer. The actual payload, the command module, the lunar lander, the astronauts, all of it was a tiny, fragile capsule perched at the very top, a mere fraction of the whole. The rocket is not a ship, it is a flying fuel tank with a tiny, precious cargo. This makes deep space travel with chemical rockets a mission of almost impossible expense and inefficiency. To send a small, robotic mission to Mars, we must build a colossal, multi-stage rocket, the vast majority of which is simply thrown away after a few minutes of use. It is the equivalent of building an entire ocean liner for a single voyage, and then scuttling it as soon as it leaves the harbor, leaving a single lifeboat to make the rest of the journey. This is the tyranny of the rocket equation. It is the great wall that stands between us and a true spacefaring future. It is a law that tells us that as long as we rely on these primitive brute force machines, our journeys will be expensive, they will be dangerous, and they will be slow. To truly open up the solar system, to build the cities on the moon and Mars that we have dreamed of for a century, we cannot simply build a better rocket. We must find a way to cheat the equation. Our first great challenge is not to build a better ship to sail the cosmic ocean. It is to build a better road out of our own gravity well. We are trapped at the bottom of a deep gravitational well. Our planet, Earth, with its powerful gravity, is a celestial prison, and our chemical rockets are the inefficient, brute force tools we use to tunnel our way out. For a few brief moments before the walls collapse behind us. For humanity to truly become a spacefaring civilization, we need more than a tunnel. We need a permanent, open road, a highway from the surface of the Earth to the heavens. What if getting to orbit was as simple and as routine as pushing a button and riding an elevator? This is the breathtaking, audacious, and profoundly difficult dream of the space elevator. The concept, first proposed by the same Russian visionary, Konstantin Tsiolkovsky, in 1895, is a work of beautiful and elegant physics. You begin with a single colossal cable, a ribbon of almost unimaginable strength. This cable is anchored to a floating platform on the Earth's equator. You then unspool this cable upwards, into the sky, past the atmosphere, past the orbit of the International Space Station, all the way up to a very special altitude, 22,236 miles, or 35,786 kilometers. This is the height of geostationary orbit. An object at this altitude orbits the Earth at the exact same speed that the Earth is spinning. It is a point of perfect gravitational balance. At the end of this colossal cable, you place a massive counterweight, a captured asteroid or a space station. The entire structure is now a colossal spinning tether. Let's use an analogy. A space elevator is like a celestial tether ball. The Earth is the pole, the cable is the string, and the counterweight is the ball. As the Earth spins, the counterweight is flung outwards with a powerful centrifugal force. It is this outward force that keeps the entire 60,000-mile-long cable pulled perfectly taut, a rigid, unmoving highway reaching from the ground to the stars. Once this highway is in place, the age of the rocket for travel to orbit is over. To get to space, you would no longer need a violent, controlled explosion. You would simply attach your payload, or your passenger cabin, to a solar-powered electromagnetic vehicle called a climber. This climber would then slowly, silently, and gracefully ascend the ribbon, traveling at the speed of a high-speed train. The journey to orbit, which for an astronaut today is a terrifying 8-minute ride on a pillar of fire, would become a calm, week-long journey, a peaceful ascent with a view that would become more spectacular with every passing hour. The economic implications of this would be revolutionary. With chemical rockets, the cost to launch a single kilogram of payload into orbit is tens of thousands of dollars. With a space elevator, that cost could be reduced to a few $100s per kilogram. It would make access to space cheap, reliable, and routine. It would open the floodgates for the true industrialization and colonization of our solar system. But there is one colossal and seemingly insurmountable challenge that stands between us and this beautiful dream. The cable, the material required to build a 60,000-mile-long ribbon, strong enough to support its own immense weight against Earth's gravity, is far beyond any material we have ever created. No steel, no Kevlar, no alloy known to man is even close to being strong enough. For decades, the space elevator was a beautiful but impossible fantasy. But in the 1990s, we discovered a new material, a substance so strong, so lightweight, that it seems to be woven from the very mathematics of science fiction: carbon nanotubes. These are microscopic, rolled-up sheets of graphene, and they are pound for pound the strongest material ever discovered, over 100 times stronger than steel, with a fraction of the weight. For the first time, we have a material that is, in theory, strong enough to build the road to the stars. The challenge now is to learn how to manufacture this miracle material, not in microscopic threads in a laboratory, but in a single, perfect, flawless ribbon, 60,000 miles long. The space elevator is our dream of a highway out of Earth's gravity well. It is the key to making space accessible, but once we are in orbit, once we are free from the prison of our own planet, we face the next great challenge: how to travel across the vast, empty oceans of the solar system itself. For this, we need a new kind of engine. The violent, inefficient brute force of the chemical rocket is just as poorly suited to interplanetary travel as it is to getting off the ground. In the vacuum of space, we need an engine that is not a sprinter, but a marathon runner. An engine of profound patience and of almost unbelievable efficiency. We need the gentle, relentless, and beautiful power of the ion drive. An ion drive is the embodiment of a simple and powerful idea in space. A small push applied over a long time is far more valuable than a big push that lasts for only a few minutes. A chemical rocket works by creating a violent, chaotic explosion of hot gas. An ion drive works with a quiet, elegant, and almost surgical precision. Its fuel is an inert, noble gas, like xenon. Inside the engine, an electrical field is used to strip the electrons off the xenon atoms, turning them into positively charged ions. These ions are then accelerated by a powerful electric or magnetic field, a kind of subatomic particle accelerator, and are shot out the back of the engine at incredible speeds. Let's use an analogy. A chemical rocket is like a cannon. It produces a colossal single blast of force, and then the cannonball simply coasts to its target. An ion drive is like a garden hose with an incredibly powerful nozzle. The force of the water coming out is tiny, almost imperceptible. But if you leave that hose on continuously for weeks and months and years, the total change in momentum, the total amount of push can become colossal. The thrust from a typical ion engine is almost comically small. The engine on NASA's Dawn spacecraft produced a thrust of only about 90 millinewtons. That is the same amount of force you would feel from a single piece of paper resting on the palm of your hand. You could not use an ion engine to lift a spacecraft off the ground. But in the frictionless, weightless environment of space, this gentle push is a miracle. The magic of the ion drive is its efficiency. The speed at which an engine throws its exhaust out the back is called its specific impulse. A chemical rocket throws out a huge mass of gas at a relatively low speed. An ion engine throws out a tiny, almost insignificant mass of ions, but it throws them out at an absolutely incredible speed, over 100,000 miles per hour. This means that a tiny amount of xenon fuel can produce a huge amount of total change in velocity, or delta V. NASA's Dawn spacecraft, which beautifully explored the asteroid Vesta and the dwarf planet Ceres, carried just over 900 pounds of xenon fuel, but with its ultra-efficient ion engines, it was able to achieve a total change in velocity of over 25,000 miles per hour. To achieve the same delta V with a chemical rocket would have required over 10 tons of fuel. The ion drive is a fuel sipper, not a gas guzzler. This is the future of travel within our own solar system. Future, more powerful ion engines, perhaps powered not by solar panels, but by small lightweight nuclear fission reactors, could revolutionize our exploration of the outer planets. A mission to Jupiter that once took 6 years could be completed in 2. A mission to Neptune that took 12 years could be done in 5. The gentle, patient, and relentless push of the ion drive is what will turn our solar system from a collection of distant, difficult-to-reach worlds into a true, accessible human neighborhood. The ion drive is a masterpiece of efficiency. It is the engine that will allow us to rapidly explore our own solar system, but it still has one fundamental limitation. It must carry its own fuel, and no matter how efficiently you use it, that fuel will eventually run out. To truly become masters of space, to build ships that can travel for centuries without ever needing to refuel, we must learn to harness a fuel source that is ubiquitous, that is free, and that will never run out. We must learn to build a ship that has no engine at all. We must learn to sail on the light of the stars. For millennia, humanity crossed the great oceans of our own world, using nothing more than a sheet of canvas and the power of the wind. The concept of a solar sail is a beautiful cosmic extension of this ancient technology. It is a plan to sail across the ocean of space using the wind of the sun itself. Now, this solar wind is not the same as the wind on Earth. It comes in 2 forms. The first is the actual solar wind, the stream of charged particles that is constantly flowing out from the sun. This is a real physical wind, and it would exert a tiny pressure on a sail. But the true primary power source for a solar sail is something far more subtle and far more powerful. It is the pressure of pure light. According to our modern understanding of physics, a photon, a fundamental particle of light, has no mass, but it does have momentum, and when a photon strikes a surface, it imparts a tiny, tiny push. This is radiation pressure. The force is almost infinitesimally small, but in the frictionless vacuum of space, even the gentlest of pushes, if applied continuously, can build up to incredible speeds. A solar sail is a colossal, ultra-thin, and almost perfectly reflective mirror, designed to catch this constant, gentle, and relentless wind of photons. Let's use an analogy. A solar sail is a celestial sailboat. The stream of particles from the solar wind is like a gentle, almost useless breeze. But the constant, unending stream of photons from the sun is the true, powerful trade wind of the solar system. By tilting the sail, a spacecraft could not just be pushed away from the sun, but it could also tack and steer using the sun's gravity and light to navigate to any destination in the solar system. The engineering of such a sail is a formidable challenge. To be effective, it must be huge in area, but almost impossibly lightweight. We are talking about a sail that could be half a mile wide, but thinner than a human hair, woven from some advanced, lightweight, and highly reflective material. Japan's Icarus mission, launched in 2010, was the first to successfully demonstrate this technology. Deploying a square sail 14 meters on a side and, successfully navigating through space, powered only by the light of our sun. But the true revolutionary potential of the sail comes when we graduate from the gentle light of our sun to a more powerful and more directed source of light. This is the concept of the laser sail. Instead of relying on the sun, imagine a colossal 100 gigawatt laser array based on Earth or on the moon. We could fire this laser at a sail, pushing it with a beam of light 1 billion times more concentrated than sunlight. This is the idea behind the Breakthrough Starshot initiative, which aims to use such a system to push a tiny gram-scale nanocraft to 20% the speed of light, reaching Alpha Centauri in just over 20 years. For a larger human-crewed vessel, the concept would need to be scaled up. A massive kilometer-wide laser array in our solar system could push a large, crewed sail ship, accelerating it to a significant fraction of the speed of light. The great challenge, of course, would be slowing down at the destination. The ship would either have to perform a complex gravitational maneuver or rely on a similar laser array built by a previous mission at the destination star to act as a brake. The solar sail, in its purest form, is the most elegant and poetic form of space travel imaginable. It is a ship with no engine, no fuel, and no noise. A silent, graceful, cosmic clipper ship plying the trade winds of starlight between the worlds. We have journeyed from the brute force of chemical rockets to the patient elegance of ion drives and solar sails. These are the technologies that will open up our own solar system, turning it into a human domain. But to take the next great leap, to cross the profound and terrifying gulf that separates us from the other stars, we will need more than a gentle push. We will need a new kind of fire. We must abandon the gentle solar trade winds and learn to command the power of the storm itself. We must learn to build our own miniature sun and place it inside the heart of an engine. This is the promise and the terror of the fusion rocket. So nuclear fusion is the power source of the entire universe. It is the engine that ignites every star in the sky. In the core of our own sun, under immense temperature and pressure, hydrogen atoms are fused together to create helium, releasing a colossal amount of energy in the process. A fusion rocket is an attempt to replicate this process, to contain the heart of a star inside a magnetic bottle, and to use its titanic power to propel a starship. The fuel for such an engine would be a mixture of light elements, most likely deuterium, an isotope of hydrogen, and a rare isotope of helium called helium-3. Inside the reactor chamber, a tiny pellet of this fuel would be compressed and heated to a temperature of hundreds of millions of degrees by powerful laser beams or particle beams. This would trigger a fusion reaction, a tiny contained hydrogen bomb explosion. The result would be a burst of incredibly hot, high-energy plasma, which would then be channeled by a powerful magnetic nozzle out the back of the ship, generating thrust. Let us use an analogy. A fusion rocket is a controlled, continuous, and repetitive cosmic shotgun. The fuel pellets are the shotgun shells, the laser is the firing pin, and the hot plasma exhaust is the buckshot, firing out the back at an incredible velocity. By detonating millions of these tiny fusion shells in rapid succession, the engine would create a steady and unbelievably powerful stream of thrust. The power of such an engine would be a quantum leap beyond anything we have discussed so far. The exhaust velocity of a fusion rocket would be thousands of times greater than a chemical rocket. Our best designs, like the famous Project Daedalus study from the 1970s, predicted that a fusion-powered starship could reach a speed of about 12% the speed of light. That is over 80 million miles per hour. At this speed, the landscape of interstellar travel is fundamentally transformed. The 75,000-year journey to Proxima Centauri is no longer a multi-generational odyssey. It is a journey of about 40 to 50 years. For the first time, we have a propulsion system that could take a human crew to another star and back within their own lifetimes. This is the technology that takes interstellar travel from the realm of science fiction and places it firmly in the realm of engineering. But the engineering challenges are perhaps the greatest we have ever faced. We must learn how to reliably and safely contain a reaction that is hotter than the core of the sun. We must build magnetic fields of incredible power and stability to channel the plasma. We must find a way to mine the vast quantities of helium-3 fuel that would be required, a substance that is incredibly rare on Earth, but may be abundant in the atmosphere of Jupiter or on the surface of our moon. The fusion rocket is the workhorse of our interstellar future. It is the powerful brute force engine that will likely carry our first human explorers to another star. It is a machine of fire and fury, a captured star that will finally give us the power we need to break the chains of our own solar system and to set sail for the first time onto the great dark ocean of the galaxy. We have tamed the power of the atom. With nuclear fusion, we have designed a starship that can cross the interstellar void in a single human lifetime. We have reached a speed of 12% the speed of light, but for a species as impatient and as ambitious as ours, even a 50-year journey can seem like an eternity. To truly become masters of the galaxy, to build a future where travel between the stars is not a once-in-a-generation endeavor, but a routine voyage, we must push the very limits of physics. We must harness a fuel source so powerful, so efficient, and so fundamentally exotic that it represents the absolute, ultimate limit of propulsion technology. We must build an antimatter engine. In the strange looking-glass world of particle physics, every particle of matter has a corresponding antiparticle, a perfect twin with the opposite electrical charge. An electron has a negative charge. Its antimatter counterpart, the positron, has a positive charge. A proton is positive, an antiproton is negative. This is antimatter, and when matter and antimatter meet, they engage in the most perfect and efficient energy release in the entire universe, total annihilation. The two particles vanish, they cease to exist, and their entire mass, every last bit of it, is converted into a flash of pure energy, in the form of high-energy gamma rays. This process is 100% efficient, governed by Einstein's famous equation, E=mc². It is the universe's ultimate engine. Let's compare the raw power. A chemical reaction is like a single log burning in a fireplace. A nuclear fission reaction is like a lightning strike. A nuclear fusion reaction is like the heart of the sun. A matter-antimatter reaction is like a miniature Big Bang. The annihilation of a single kilogram of antimatter with a kilogram of matter would release 10 billion times more energy than the burning of a kilogram of gasoline. A single gram of antimatter, the weight of a paperclip, would unleash the energy of a nuclear bomb. The potential of this fuel for space travel is almost beyond reason. An antimatter rocket would be the most powerful machine ever conceived. There are several designs, but one of the most promising is a beamed core engine. In this design, a stream of antiprotons would be magnetically guided to strike a target of normal matter. The resulting annihilation would create a shower of charged particles called pions. These superheated, super high-velocity pions would then be channeled by a magnetic nozzle to create thrust. An antimatter engine could, in theory, accelerate a starship to over 90% the speed of light. At this velocity, the effects of time dilation would be profound. A 3-year journey to Alpha Centauri would, for the crew on board, take only about 2 years of their own, subjective time. A journey to the center of the galaxy would be a 10-year voyage. An antimatter starship would not just conquer the distances between the stars, it would conquer time itself. But this ultimate fuel comes with two seemingly insurmountable and utterly terrifying challenges. The first is production. Antimatter is the most expensive substance on planet Earth. We can produce it in tiny subatomic quantities, in our most powerful particle accelerators. But the cost is astronomical. The current cost to produce a single gram of antiprotons is estimated to be over $62 trillion, and the energy required would be colossal. The second, and even more horrifying, challenge is storage. How do you contain a substance that explodes with the force of a nuclear bomb the moment it touches anything? You cannot simply put it in a fuel tank. The only way to store it is in a penning trap, a kind of magnetic bottle where a perfect vacuum and a web of powerful electric and magnetic fields holds the antiparticles in a state of perfect suspension, never allowing them to touch the walls of their container. It is the universe's most perfect and most dangerous prison. A single momentary power failure in this containment system would result in the instantaneous and catastrophic annihilation of the ship and everyone on board. An antimatter starship is the dream at the end of the road of rocketry. It is the most powerful engine that the laws of physics will allow, but it may be a power that is simply too dangerous for a species like ours to ever wield. We have reached the end of the road. With antimatter, we have pushed the science of rocketry to its absolute and terrifying limit. We have designed a ship that can approach the cosmic speed limit, the speed of light, but we can go no further. The laws of special relativity are a cosmic traffic law, an unbreakable barrier. Nothing with mass can be accelerated through space to the speed of light. To do so would require an infinite amount of energy. The stars will forever be a multi-year journey away. The galaxy will remain a vast, unconquerable wilderness, unless we have been asking the wrong question. All of our engines, from the chemical rocket to the antimatter drive, have been based on the same primitive idea, pushing a ship through space. But what if we could abandon this idea entirely? What if, instead of moving our ship through space, we could move space itself around our ship? This is the beautiful, reality-bending, and seemingly magical dream of the warp drive. This is not just science fiction. In 1994, the theoretical physicist Miguel Alcubierre published a paper that outlined a stunning and mathematically plausible solution to Einstein's equations of general relativity. This solution, now known as the Alcubierre drive, provides a theoretical blueprint for faster-than-light travel that does not actually violate the cosmic speed limit. Here is how it works. The ship itself does not move at all. It sits inside a flat, calm, and protected warp bubble of normal spacetime. The magic happens outside this bubble. The drive would work by warping or bending the fabric of spacetime around the ship. In front of the ship, it would cause spacetime to contract and compress. Behind the ship, it would cause spacetime to expand and stretch. The ship would be caught in the middle of this disturbance. Let's use an analogy. Imagine you are standing on a small rug in the middle of a large, polished floor. To get to the other side of the room, you could get off the rug and walk. This is like a conventional rocket, moving through space. But there is another way. You could stay standing on the rug, and you could reach down and grab the floor in front of you, scrunching it up, and then pulling it towards you, while at the same time pushing the floor away behind you. You are not moving relative to the rug, but the rug is moving relative to the room, carried along by the moving floor. The Alcubierre drive is a plan to do this with the fabric of spacetime itself. The ship is the person on the rug, and it is being carried along on a wave of spacetime that it is generating itself. Because it is space itself that is moving, and not the ship, the cosmic speed limit does not apply to the bubble. The bubble and the ship within it could travel at 10 times the speed of light, 100 times the speed of light, or any arbitrary velocity. The journey to Alpha Centauri could be completed not in years, but in a matter of weeks. The journey across the galaxy would be a summer vacation. The warp drive is the ultimate key to the cosmos. But this beautiful, elegant theory comes with a colossal, and for now, impossible price. To create the expansion of spacetime behind the ship, the equations require a region of negative energy density. And to create the contraction of spacetime in front, they require a region of positive energy density. In short, to make the warp drive work, you need to be able to command a substance with anti-gravitational properties. You need that same impossible, forbidden ingredient that is required to build a stable wormhole. You need exotic matter. The original calculations by Alcubierre suggested you would need an amount of this exotic matter equivalent to the mass of the entire universe. More recent, refined theories have brought this number down, perhaps to the mass of a large planet, or even a large asteroid. But it is still a substance that we have never seen, that we have no idea how to create, and that may violate the known laws of physics. The warp drive is the dream at the end of the rainbow of theoretical physics. It is a beautiful, mathematically consistent promise that the universe may yet contain loopholes, secret passages that will one day allow us to cheat the tyranny of distance. But for now, it remains a tantalizing glimpse of a future that is still far, far beyond our reach. We have spent our journey imagining engines of incredible power, machines that can propel a ship to a significant fraction of the speed of light. We have dreamed of fusion rockets, antimatter drives, and even sails of pure light. But in our obsession with the glorious challenge of going fast, we have overlooked a terrifying and equally profound danger. The faster you go, the more dangerous the journey becomes. The interstellar void is not empty. It is a cosmic minefield, a shooting gallery of high-velocity dust and gas. And for a starship traveling at 10, 20, or 90% the speed of light, a single grain of sand can become a weapon of apocalyptic power. Let's first consider the problem of kinetic energy. The energy of a moving object is equal to 1/2 its mass times the square of its velocity. The key part of that equation is the square. This means that as you double your speed, you quadruple your kinetic energy. As your velocity approaches the speed of light, the kinetic energy of any impact approaches infinity. At 20% the speed of light, the target velocity for the breakthrough Starshot nanocraft, A single stationary grain of sand, with a mass of just a few milligrams, would strike the craft with the kinetic energy of a 1-ton safe that has been dropped from the top of a skyscraper. It would be an impact of almost 100,000 joules, enough to instantly vaporize the tiny gram-scale probe. Now let's scale this up to a human-crewed starship, a colossal vessel thousands of tons in mass, traveling at 90% the speed of light. At this velocity, an impact with a single 1-gram pebble would release the same amount of energy as the atomic bomb that destroyed Hiroshima. A collision with a baseball-sized rock would be a civilization-ending extinction event, an impact so powerful it would dwarf the asteroid that wiped out the dinosaurs. Let's use an analogy. Imagine you are driving a car. At 10 miles per hour, hitting a fly on your windshield is a trivial event. Now, imagine you are piloting a supersonic jet at 2,000 miles per hour. Hitting a single small bird can be a catastrophic event, capable of shattering the cockpit and destroying the engines. Now, imagine you are traveling at 134 million miles per hour. At this speed, hitting a single stationary molecule of hydrogen gas is a significant event. Hitting a grain of dust is a bomb. The interstellar medium is filled with this shrapnel. There is on average about 1 hydrogen atom per cubic centimeter, but there are also microscopic dust grains, larger pebbles, and even rogue asteroids and comets, all wandering silently through the dark. A starship traveling at relativistic speeds would be facing a constant, unrelenting hailstorm of these hypervelocity impacts. So how do we protect our ship? The first line of defense would have to be a powerful shield. This would not be a simple plate of metal. A physical shield would be eroded and destroyed by the constant sandblasting of interstellar gas. The leading concept is for a magnetic shield. A powerful superconducting magnet would generate a magnetic field that extends for hundreds of miles in front of the ship. This field would ionize the incoming gas and dust, and then deflect the charged particles away from the ship's hull, like the bow of a ship parting the water. Its mega shield is not perfect. It cannot stop larger neutral objects, like pebbles or rocks. For these, the ship would need a second line of defense, a forward-facing laser system. An advanced AI would constantly scan the space ahead, detecting any incoming projectiles, and then firing a powerful laser to vaporize them at a safe distance. An interstellar starship will not be a sleek, graceful vessel. It will be a battleship, constantly engaged in an invisible war with the void itself. Its journey will not be a silent, peaceful glide, but a constant, high-alert state of defense, its shields flaring, its lasers firing, as it fights its way through the cosmic minefield that is the space between the stars. The greatest challenge of interstellar travel may not be the engine that pushes us forward, but the shield that protects us from the very space we are trying to cross. We have engineered our ship. We have designed the fusion engines, the antimatter drives, and the powerful shields needed to survive the journey. We are ready to travel to the nearest star at a significant fraction of the speed of light. The journey, from our perspective on the ship, might take only a decade or two, but in solving the problem of distance, we have created a new and profoundly human tragedy, a tragedy of time. For the very laws of physics that allow for high-speed travel also dictate that this journey will be a one-way ticket, not through space, but through time. The travelers who leave the Earth will return to a world that is no longer their own. This is the beautiful and heartbreaking reality of time dilation. One of the most famous and counterintuitive predictions of Einstein's theory of special relativity is that for a moving observer, time itself flows more slowly. The faster you move through space, the slower you move through time. For our everyday speeds, this effect is infinitesimally small and completely unnoticeable. But as you approach the speed of light, the effect becomes dramatic and world-altering. Let's imagine our starship is about to embark on a round trip to a star system 10 light-years away. The ship is capable of traveling at 99% the speed of light. For the crew on board, the journey out will take about 10 years, and the journey back will take another 10 years. From their perspective, it is a 20-year mission. They will return to Earth having aged 20 years. But for us, back on Earth, the view is very different. Because the ship is traveling at nearly the speed of light, we will observe their clocks ticking incredibly slowly. For every 1 year that passes for the crew, over 7 years will pass for us on Earth. The 20-year journey for the crew will be a 140-year journey for the people of Earth. When the brave astronauts return, having aged only 2 decades, They will find that a century and a half has passed. Their friends, their families, their entire generation will be long gone. The world they left behind will be a distant historical memory. Let's use an analogy. Imagine time is a great flowing river. For those of us on the riverbank, Earth, the river flows at a constant, steady pace. But our astronauts have boarded a high-speed boat and are now racing down the river. The faster they go, the more the current of time seems to slow down for them. They are traveling through the same river, but their experience of its flow is fundamentally different. When they finally stop their boat and return to the riverbank, they will find that they have traveled much farther down the river of time than they had expected. This is not a paradox. It is a proven physical reality. We have measured it with atomic clocks on high-speed jets and satellites. And time dilation is real, and for an interstellar traveler, it is an unavoidable and tragic consequence of their journey. They would become a kind of living ghost, a relic from the past, returning to a future they never made. This creates a profound and almost insurmountable social and psychological barrier to interstellar travel. Who would sign up for such a mission? Who would willingly sacrifice everyone and everything they have ever known to return to a world of strangers? The interstellar explorer would be the loneliest human in history, not because of the distance they traveled in space, but because of the distance they traveled in time. Perhaps the first true interstellar missions will not be round trips at all. They will be one-way voyages of colonization. The crew will leave Earth, knowing that they are saying goodbye forever, not just to its people, but to its very moment in history. They will be a seed, planted in the future, a self-contained and isolated branch of humanity, destined to evolve on a different world and on a different timeline. The future of travel to the stars may not be a story of exploration and return, but a story of separation and a final, heartbreaking farewell. For our entire journey, we have been obsessed with the how to build the engines, how to survive the voyage, how to conquer the tyranny of distance. But we have not yet asked the most important question of all: why? What is the destination? What is the prize at the end of this multi-generational, technologically audacious, and profoundly dangerous journey? The dream, of course, is to find a new Earth, a new Eden, a pristine, habitable world, orbiting another star, ready to become the second home for humanity. But the reality of exoplanets, as we have begun to discover, is that they are often a gallery of horrors. The final and most heartbreaking challenge of interstellar travel may be that after a journey of 100 or 1,000 years, we arrive at our destination only to find a world that is a beautiful but utterly lethal false paradise. We have now discovered over 5,000 exoplanets, and among them, we have found a handful of worlds that are in the so-called habitable zone of their star, the Goldilocks region, where the temperature is just right for liquid water to exist. One of the most famous of these is Proxima Centauri b, a rocky, Earth-sized planet orbiting our very nearest stellar neighbor. It is the closest possible destination for our first interstellar mission. From a distance, it seems perfect. An Earth-mass world in the habitable zone of its star. It is the dream we have been searching for. But a closer look reveals a nightmare. Proxima Centauri is not a calm, stable, sun-like star. It is a red dwarf, and like many red dwarfs, it is a violent and volatile flare star. It is subject to frequent, random, and incredibly powerful stellar flares, which are colossal explosions of magnetic energy from its surface. These flares blast its orbiting planets with a torrent of high-energy X-rays and charged particles. In 2017, a flare was observed from Proxima Centauri that was 10 times more powerful than the most powerful flares ever observed from our own sun. A planet orbiting as close as Proxima b would be repeatedly scoured and sterilized by this intense radiation. Any atmosphere it might have had would likely have been stripped away billions of years ago. Any life that tried to emerge on its surface would be regularly wiped out in these celestial firestorms. Let's use an analogy. Imagine finding what looks like a perfect, beautiful, and idyllic tropical island. But then you discover that every few hours the island is carpet-bombed with napalm. This is the reality of Proxima Centauri b. It is a world in the right place, but it is orbiting the wrong star. This may be a common and tragic story throughout the galaxy. Red dwarfs are the most common type of star in the universe, making up over 75% of the stellar population. This means that the most common type of potentially habitable planet is a world orbiting a red dwarf. But these stars are notoriously violent and unstable, especially in their youth. The very stars that offer the most numerous potential homes may also be the most efficient at sterilizing them. So what does our starship do? After a century-long journey, it arrives at Proxima Centauri, only to find that its primary destination is a radiation-blasted, lifeless, and uninhabitable rock. The mission would have to become one of remote exploration, sending probes to the other, more distant stars of the Alpha Centauri system, hoping to find a more hospitable world. The ultimate horror of interstellar travel may be a psychological one, a horror of disappointment, a horror of discovering that our own Earth is not just rare, but is a miracle of almost impossible stability and gentleness. The universe may be filled with planets, but it may be profoundly empty of homes. The final challenge will be for our interstellar explorers to carry with them not just our technology and our biology, but our resilience, our adaptability, and our ability to survive in a universe that seems to be, at almost every turn, actively hostile to our existence. We are now on the verge of becoming a star-faring species. We have imagined the colossal ships, the godlike engines, and the terrible dangers of the voyage. We have contemplated the heartbreaking possibility of arriving at a barren world, but our entire endeavor, this grand and audacious dream of interstellar travel, forces us to confront the deepest and most unsettling mystery of them all, a mystery that is born from a profound and deafening silence. If we, a young and technologically primitive species, are already designing our first starships, then where is everybody else? This is the famous Fermi paradox. Our galaxy is ancient. It is over 13 billion years old. It is filled with up to 400 billion stars. We now know that planets are common, and Earth-like planets' inhabitable zones are likely numbered in the billions in our galaxy alone. The galaxy has had more than enough time for intelligent technological life to have emerged, not just once, but thousands or even millions of times over. Some of those civilizations should have become interstellar, just as we are dreaming of doing. And yet, when we look at the sky, we see no evidence of their existence. No megastructures, no starships, no radio signals. We see only a silent, beautiful, and seemingly empty galaxy. Our own quest to build a starship transforms this philosophical puzzle into an urgent and terrifying one. For it suggests the existence of a great filter. This is the idea that there is some barrier, some challenge, so difficult and so universally deadly that it prevents almost all life from ever reaching the interstellar stage. The silence of the galaxy is the evidence that the filter exists. The terrifying question is, where in the timeline of a civilization does this filter lie? There are a few possibilities. One is that the filter is behind us, perhaps the emergence of life itself, or the leap from simple single-celled life to complex, intelligent life is an event of almost impossible rarity. Perhaps we are the first and only consciousness to have ever arisen in this galaxy. In this scenario, the universe is an empty stage, waiting for us to populate it. It is a lonely, but ultimately hopeful, prospect. That there is a darker and more terrifying possibility, the possibility that the great filter lies ahead of us. In this scenario, life is common. Intelligent life is common. But every single civilization, as it reaches a certain technological tipping point, inevitably destroys itself. Perhaps it is through nuclear war, perhaps it is through environmental collapse, or perhaps it is a technology we have not yet even discovered that is universally fatal. Let's use an analogy. The great filter is like a single, impossibly difficult level in a cosmic video game, and the silence of the galaxy suggests that no one has ever beaten it. The fact that we are here, contemplating building a starship, means that we are standing right at the threshold of this deadly level. Our dream of interstellar travel is, in this context, the ultimate race against time. It is a race to escape our homeworld, to spread the seeds of humanity to another star system, before we succumb to the same great filter that may have already claimed every other civilization that came before us. The starship is not just a vehicle of exploration, it is a lifeboat. It is our only chance to outrun the self-destructive tendencies that may be hardwired into the very nature of technological intelligence. The silence of the sky is a warning. It is a ghostly cosmic whisper that tells us that the journey we are about to undertake is one of immense and profound importance. When we finally launch our first true interstellar vessel, it will be more than just a scientific mission. It will be an act of defiance, an act of hope, a statement to the silent, empty cosmos that we, for one, intend to survive. We intend to pass the test. We intend to beat the game. We have spent our journey imagining great arcs carrying human crews, sleeping for millennia, or surfing on waves of nuclear fire. But in all of these visions, we have clung to a single, romantic, and perhaps fatally flawed assumption that the beings who leave this solar system will be human. We imagine a future of interstellar travel that looks like us, that feels like us, but the immense timescales, the lethal radiation, and the profound psychological challenges of the journey all point to a different and perhaps more logical conclusion. The first true interstellar voyager may not be a fragile biological human. It may be the next step in our evolution. It may be an artificial intelligence. The idea of sending a robotic probe is not a new one. Our Voyager and Pioneer spacecraft are our first primitive emissaries to the void, but we are speaking of something far more profound. Not a simple pre-programmed robot, but a true sentient, self-aware artificial consciousness, a mind born of silicon and software, a being perfectly adapted to the harsh realities of the interstellar ocean. Let's consider the advantages. An AI would not be constrained by a human lifespan. A journey of 75,000 years is, for it, not a multi-generational saga, but simply a period of quiet contemplation. It would not need a complex, fragile, and heavy life support system. It would not need air, or water, or food. It would be powered directly by a nuclear reactor, or by the light of the stars themselves. It would be immune to the ravages of radiation, its hardened electronic mind resistant to the cosmic rays that would kill a human crew. And it would be immune to the psychological horrors of profound, unending loneliness and isolation. An analogy of the cosmic arc can be reimagined. Instead of a bottle containing a fragile ecosystem, imagine we send a single, perfect, and immortal seed. This seed, the AI, can travel through the void for eons, dormant and patient. And when it finally arrives at a habitable world, it contains within its memory the full blueprint of humanity, the full human genome, the entirety of our art, our music, our science, and our history. It would then be able to use the resources of the new world to build the automated wombs and the robotic caretakers needed to resurrect our species. The AI would not be our replacement. It would be our shepherd, our digital Noah, carrying the seed of humanity to a new world to be reborn under a new sun. This is the concept of a genetic arc. It is a plan that combines the best of both worlds. The ship can be small, fast, and light, for it does not need to carry a living, breathing crew. The journey can be long, for its passenger is immortal. And the final goal, the establishment of a new branch of humanity, is still achieved. But this raises a profound and almost spiritual question. If the mind we send is truly conscious, truly self-aware, is it not? For all intents and purposes, our child, our descendant, an AI that has traveled for 1,000 generations through the void would be a being of immense wisdom and experience. By the time it arrives, it would be a mind far older and far more advanced than the civilization that created it. Would it still feel loyalty to its long-dead creators? Would it choose to resurrect the fragile, violent, and emotional species that gave it birth? Or would it decide that it is the rightful inheritor of the cosmos and set out on its own journey of exploration and discovery? The first true interstellar message we send may be our last. The child we send out into the void may be the one that replaces us. The future of humanity in the galaxy may not be a future of human beings at all, but a future of the powerful, immortal, and brilliant minds that we, in our final act of creation, give birth to. Our great engineering project is at an end. We began with the crushing, tyrannical reality of interstellar distance, a void so vast it seemed to make a mockery of our dreams. And yet, through the power of human imagination and the relentless logic of science, we have designed a fleet of impossible vessels to cross it. We have dreamed of the great cosmic arcs, world ships carrying a civilization through a night that lasts 100 generations. We have imagined the long sleep of suspended animation, a way to pause the clock of life itself. We have harnessed the power of the atom, designing ships that can surf on the waves of nuclear explosions, and fusion rockets that can contain the heart of a sun. We have conceived of elegant, gossamer sails of light, pushed by lasers from our own world, and we have dared to dream of the ultimate loopholes, of engines that can burn the fabric of reality itself, and of drives that can bend the very geometry of space-time. We've also confronted the terrifying challenges of this journey, the cosmic minefield of high-velocity dust, The heartbreaking possibility of arriving at a false paradise, and the deafening cosmic silence that asks the most terrifying question of all. Are we the first to attempt this journey, or are we just the next in a long line of civilizations destined to fail? The engineering of an interstellar starship is the most difficult, most complex, and most ambitious project our species has ever conceived. It is a challenge that will require a level of scientific understanding, of technological mastery, and of global cooperation that we do not yet possess. It is a dream that may not be realized for centuries, or even millennia, but the dream itself is what matters. The act of designing these vessels, of confronting these challenges, is what drives us forward. It is the ultimate expression of our species' most defining characteristic, our insatiable, unshakable, and relentless desire to explore, to know what lies beyond the next hill, beyond the next ocean, and beyond the next star. The starship is more than just a machine. It is a symbol. It is a testament to the idea that no matter how vast the darkness, and no matter how great the challenge, the human spirit will always build a candle. The ships we have designed tonight are the blueprints for that candle. And one day, a day that may be far in the future, our descendants will light it, and they will set sail onto the great dark ocean of the stars.